Thanks everyone for staying till the end of this conference, especially when there's no free food provided on Thursdays. So actually, I would like to talk about tides in double white dwarfs. I actually talked about this during the conference, so sorry about the repetition, but hopefully it reminds people a little bit, and hopefully it's going to be new for people who just attend the conference. So white dwarfs or white dwarf binaries, they are important for various reasons. For example, during this conference, we heard a lot about, they are potential progenitors for type 1a supernova or supernovae. So for many reasons, for me, I'm mostly interested in them because they are guaranteed sources for multi-messenger astronomy. We can simultaneously observe a white dwarf in both gravitational wave and also electromagnetically, for example, in optical. And it has been estimated, I believe, by people here in the audience, like there will be something around 100 or so double white dwarf binaries can be observed in a multi-messenger sense. So it's going to be exciting for us to consider the potential synergy we can get by combining both the GW and optical data together. And for today, I would like to highlight the role of tides in this game. Basically, tides can modify the frequency evolution rate of a GW signal. It can also excite some orbital eccentricity. And then in optical, tides can induce pulsations in light curves. So to see the significance of the tide, let's first consider its impact on the orbital decay of a double white dwarf system. Suppose we have LISA. We can then monitor the gravitational wave signal from a double white dwarf for maybe a few years. And then over this period, we can measure the orbital decay of the binary. The first thing we can get there is is f dot, basically the first time derivative of the frequency. From this thing, we measure the chirp mass of the system. So the chirp mass is the specific combination of component masses. At this point, we cannot yet separate out matter effects. But if the white dwarf is sufficiently compact, or if the binary is sufficiently compact, if it has a GW frequency, say, greater than 3 millihertz or so, then the binary can actually decay quite a bit during a few years or within a few years. And for those systems, we can measure not only f dot, but also f double dot, f triple dots, all those like higher derivatives. And such a compact binary is actually not so rare. It's been estimated that about half or nearly half of the individually resolvable white dwarf binaries will have a GW frequency greater than 3 millihertz. So for those systems, we can see the impact of the tide. The physics is the following. For those compact binaries, we would expect tidal synchronization to happen. Here, by synchronization, really what I mean is that the spin rate of a white dwarf will evolve at the same rate as the orbital frequency. And the difference between the spin frequency and the orbital frequency will stay roughly constant. So this simple synchronization condition actually dictates the amount of energy transfer from the orbit to the rotational energy of the white dwarf. And because of this excess energy transfer, it accelerates the decay of the orbit compared to the point particle case. And from this plot, for those compact white dwarfs, this effect can actually modify the point particle frequency decay rate by something like 10%-ish. And that's actually a quite strong effect. Basically, by measuring this excess frequency evolution, we can measure the moment of inertia of the white dwarf. So for the compact ones, for the compact binaries, if the orbital frequency is smaller than something like 5 minutes or so, we can actually achieve percent level accuracy in terms of determining the moment of inertia of the white dwarf. Alternatively, if we trust our models of white dwarfs, we can then write the moment of inertia as a function of the mass of the white dwarf. And then using this relation, we can then probe the component masses within this binary. Recall that from the point particle GW radiation, we can only measure the chirp mass, which is a specific combination of the component masses. And now, including the tidal effect, we probe another combination of the masses. And then combining the two, we can now individually determine the values of M1 and M2. And this can be important because from that, we can say if the system's total mass exceeds the Chandrasekhar limit or not, and of course, there are many other things we can do from this, knowing the individual component masses. And then, besides affecting the orbital decay, we can also measure the effect of the tide through its impact on the equilibrium configuration of the orbit. So in gravitational wave signals, this is manifested as the excitation of small orbital eccentricity. And then in optical signal, this leads to positions in light curves. So let's first consider the gravitational wave signal. Just like, when we have tidal interactions, the tide will deform the white dwarf into an elliptical shape. And then this same effect, when it backreacts on the orbit, it will also deform the orbit to be a little bit eccentric. What that means is that when we consider the gravitational wave radiation from such a system, the gravitational wave signal will be emitted not only at twice the orbital frequency, but also at other orbital harmonics, as indicated by the blue peaks here. And the physics here is actually the same as how the tide modifies the in spiral of a binary neutron star signals, which we already measure with LIGO. And from the height of those peaks, we measure the tidal deformability of a white dwarf, basically the log number times radius to the 5th power. The same effect can also be seen in optical. So this corresponds to the ellipsoidal variability of the light curve. The physics is illustrated in the cartoon here. Basically, the tide changed the shape of the white dwarf. That modulates the brightness of the light curve. If the emitting area of the white dwarf is greater towards the observer, then the white dwarf, then the light curve will appear brighter. And from the cartoon here, we see that this ellipsoidal variability should vary at twice the orbital frequency. And one thing is that this signal will be in phase with the eclipsing signal if the binary eclipses. So basically, each time when the binary eclipses, we should see the ellipsoidal variability or this position to be at its minimum, because the white dwarf has the smallest emitting area towards the observer. And using this effect, we can measure the mass ratio of the system. And this can be important because recall that from the gravitational wave signal, we can measure the chirp mass. If we get the mass ratio from the optical observation, then we now can individually determine the values of M1 and M2. So there's one caveat though. We need to be a bit careful when we interpret this light curve position, because the dynamical tide can also induce a signal at twice the orbital frequency. And here by the dynamical tide, what I mean is that in this case, the tidal field mostly produces a non-adiabatic perturbation of the temperature of the white dwarf, whereas the ellipsoidal variability is mainly, its effect is mainly changing the size of the white dwarf. But this time, the dynamical tide is non-adiabatic, it changes the temperature. If we don't account for this effect carefully, then it will bias our mass ratio estimation assuming ellipsoidal variability. One example is this system J0538. It has a 14-minute orbital period, and here the hotter white dwarf is really hot. It's something like 26 kilokelvin. When the authors initially tried to fit this position curve as ellipsoidal variability, they infer a not so physical mass ratio. But really, we should explain this signal with dynamical tide. And here, the smoking gun evidence is the phase. As we said earlier, if this position is due to ellipsoidal variability, then when the binary eclipses, the signal should be at its minimum. But here, the signal actually crosses zero. So this phase lag cannot be produced by the ellipsoidal variability, but it indicates strongly a dynamical tide origin of the signal. And this is an example illustrating the importance of having good theoretical models when we're interpreting different signals. And that's pretty much all I want to say. So here is my summary slide. On the left, I show a very incomplete sample of different measurements we can make in both gravitational wave and also electromagnetically. So we talked about things in gravitational wave quite extensively. In terms of EM, I just mentioned the position. And then from all those different measurements, we can get quite a lot of information out. If we can synthesize all those information together, we can know both the properties of the white dwarf itself and also the property of the binaries. So I think that's kind of exciting. And yeah, that's all I want to say. And yep.
Questions? So from which period do you expect the tides to be dominant, and from which period they should be taken into account?
Basically, 3 millihertz.
Okay.
So that's roughly here. So kind of for different reasons, like above 3 millihertz, we start to individually resolve the white dwarf. And then above 3 millihertz, tide starts to, for those systems, we can measure, F double dot. And then for those systems, tide can, accelerate the orbital decay by something more than % level or nearly 10%-ish. So roughly, I would say 3 millihertz.
And that will be already visible in the light curve.
For the light curve, things are, we can see this effect at larger separations. So basically something like 10 minutes or 20 minutes, the ellipsoidal variability is already important there.
Thanks for the talk. So we have one binary HM concrete where we have measure F dot dot now. How does that help in your scenario? Does that mean we can get something more from gravitational wave measurements, for example, if we already have the F dot dot?
Yeah, yes. So because at if we measure F double dot, we can then test if that's, say, consistent with pure point particle GW radiation. And then if we see excess, then, is it due to tide? Is it due to some other effects? So, yeah.
Yeah, Jim?
So first, a quick comment. HM Cancri is mass transferring, so the F double dot may tell us more about mass transfer than tides.
Oh.
A question, Hong. So you said you can measure the moment of inertia. That assumes that this theory is correct, right? So
yep.
Do you have any suggestions about how we verify tidal theories without making that assumption?
Well, I guess one thing is that in this case, we did had a, let's say, if the system is synchronized, we have a clear power law, or I'll say like, we know the tidal energy transfer as a function of frequency. So if the difference between f double dot and f dot is consistent with that, you know, after removing the GW contribution, is that consistent with this power law predicted by, you know, requesting tidal synchronization? That's probably one thing. And then for white dwarf, we have some rough idea about their moment of inertia. So it shouldn't be so far off.
Yep. Okay, thanks.
Valeria?
And also, thank you for the nice talk. I wonder, so you said before that the tides starts matter from 3 millihertz onwards, and I guess that also depends on the binary mass.
That's correct.
I wonder how that dependence go in the frequency mass parameter space. Yeah, it would be nice to have that plot. I would love to have it on my desk.
Yeah. So here I did cheat it a little bit by assuming like, you know, 0.6 type of things. So I mean, for those systems, they evolve a little bit, so it's easier to measure f double dot. If we have like more, you know, like a 0.3 helium plus like 0.6 CO, we need to go to slightly higher frequency to see f double dot, but there the tide is also stronger because the helium one is, it experiences the tide more. Yeah, it's puffier. Yeah, but yeah, that's something we should. So instead of doing like a 1D plot, it's better to do a 2D.
Any more questions for Hank? If not, thank you very much.
Okay, on behalf of the organizers, I wanted to thank you all very much for coming and sharing your science and hanging out. I've had a great time catching up with old friends and meeting new people, and I hope you have had a good time too. So safe travels, and I hope we all see each other soon. And that, the conference is over.